Hi everyone. So here we are on chapter 18 and this is section 2, which is on concentration of solutions. So the concentration of a solution depends on the amount of solute versus the amount of solvent. Okay? Remember, you have to have both of those components in order to have a solution. So if something is dilute, so here's dilute. So if something is dilute, that means it has a low concentration of solute, which means therefore it has a lot of solvent, okay, or a lot of water, right? And then on the other hand, if something is concentrated, it has a high concentration of solute and then very little solvent, okay? So dilute and concentrated will basically tell you the difference between the amount of solute in the solution. We use the term molarity to represent concentration of solutions. So for molarity, we use a capital M here. Okay, so that is the abbreviation for molarity, and this equation will need to be memorized. So you should highlight it, put a star next to it to memorize it. So the equation is moles of solute per liters of solution. So in other words, we say that the molarity is moles per liter. Okay, moles per liter. So now we're going to do a practice problem involving this equation. Okay, so a saline solution contains 0.9 grams of sodium chloride in exactly 100 mils of solution. What is the molarity of the solution? All right, so we're going to use our molarity equation. So molarity equals moles per liter. Okay, so we read the question. Well, it gives us grams and it gives us milliliters, right? So the milliliters of solution, we can convert that into liters. So you're going to move your decimal 3 places to the left. 1, 2, 3. So it's going to be 0.1 liters for the volume. But notice that it gives us grams and not moles. So we have to convert the grams into moles. So we're going to use your periodic table, find the molar mass of sodium chloride. Okay, so remember, if we start off with grams here, then we want grams on the bottom of the next step, and then the moles are going to go on top here. So on your periodic table, add up sodium chloride and put that number there. So let's go ahead and do that. So if you add up sodium chloride correctly, you should get approximately, pen option, you should get approximately 58.45 grams. Okay, so notice here that the grams will cancel. All right, so that will give us our answer in moles. So put that into your calculator. So 0.9 divide by 58.45, and I get that to turn out to be approximately 0.015 moles. Okay, so I'm going to put that on top over here in this molarity equation. So 0.015 moles. All right, so now we're going to divide both of these numbers. So 0.015 divided by 0.1. Okay, and then you should get 0.15. And then molarity, okay? So you can leave it as just a capital M for the units for molarity, or you can actually write out moles per liter, okay, or moles over liters, and that's fine. Both of those would be correct, all right? And then don't forget you wanted to round your answer to the proper number of sig figs. So if we look here, that contains 2 sig figs because leading zeros do not count. And then this number down here only has 1 sig fig. So when you are dividing, you're going to round your answer to the one that has the least number of sig figs. So then instead of 0.15, then we should really round that to be 0.2 molarity so that it only has 1 sig fig. Okay? All right, so now let's go on to the next problem. All right, so in this next problem, how many moles of solute are present in 1.5 liters of 0.24 molarity of sodium sulfate. Okay, so the question is how many moles, and then you're given volume and you're given molarity. So I want you to go ahead and use your molarity equation and see if you can solve this on your own. All right, so you are going to use your molarity equation. Molarity equals moles per liter. All right, so let's see what information we have that's provided in the problem. Well, the question is how many moles, okay? So we're solving for moles this time. All right, so we have molarities given to us. It's 0.24. We're solving for moles, so we can say that's X. And we are given the volume, and lucky for us, it is already in liters. Okay, so now we're just going to solve for X. So then to solve for X, you're going to do the opposite operation on both sides. So then if we have 1.5 on the bottom here, then we're going to multiply by 1.5 on both sides, right? Multiply by 1.5 here, and then multiply by 1.5 on this other side over here also, right? So you're going to multiply by 1.5 on both sides, so it crosses out here, right? So it crosses out there, and then now we can solve for X because we got X by itself. So then now you're going to put this into your calculator. All right, so let's see, 1.5 times 0.24. Okay, and then if you did it correctly, you should get 0.36, and the units are moles, because it was asking for moles, right? Okay, so you should just double check my math to make sure I did it correctly, and then that has 2 sig figs. This also has 2 sig figs, so we're going to keep our answer with 2 sig figs. Okay, this is another type of concentration problem that you'll have to know how to do, and this is dealing with dilutions, okay, dilutions. So this equation also will need to be memorized, okay, M1V1 equals M2V2. So M stands for molarity, V stands for volume, and it basically tells you right here what you're doing in the equation. So when you're doing a dilution, look, moles of the solute before the dilution equals the moles of solute after the dilution. So that means that the moles are going to be the same, okay? So the amount of moles that you start out with are going to equal the amount of moles that you end up with. So look how it has molarity times volume. Don't forget, molarity is moles per liter. So basically you're taking moles per liter times liters, right, which is volume. See how the liters cancel? And you get moles. So that's how this equation, or this is what the equation's basically telling you. The moles are equal, okay? The moles you start out with are going to equal the amount of moles that you end up with. So this is a typical dilution question that you might come across. How many milliliters of a stock solution of 2 molarity magnesium sulfate would you need to prepare 100 mils of 0.4 molarity magnesium sulfate? So what this problem is asking us to do, well, we have what is called a stock solution. Stock solution, which is also known as a standard solution, basically is the solution that is typically of higher concentration. So we have what are called stock solutions on our shelves, and those are a higher concentration because they are easy for us to dilute. All we have to do is add water if we want to dilute something, right? So notice in this problem, we're starting off with a 2 molarity, and then eventually we're going to dilute it down to make a 0.4, okay? So you have done dilutions before, I'm sure you have, you just didn't realize you were doing a dilution. So if you have ever bought one of those like frozen cans of juice, like at the grocery store, you know, that is very concentrated. It contains a lot of solute, okay? For example, let's say you got orange juice, okay? So you get that concentrated frozen juice stuff, and then what do you do to dilute it? You add water, right? It tells you to add like 2 cans of water or something, and you dilute it down. So that's basically what you're doing here, okay? We're taking something that's very concentrated and we're going to dilute it by adding water, and we want to make a 0.4. All right? So we're going to go ahead and set up the equation. M1V1 equals M2V2. So now as you're reading the question, you can start placing the variables where they belong. So this is similar to the P1V1, the gas law equations that we've done with the ones and the twos. So like the before conditions and the after conditions. So it doesn't necessarily matter which set of data you designate as your ones or your twos, just as long as they are paired up correctly. Okay, so this question here, how many milliliters, so that's volume, okay, of stock solution to molarity, okay? So then to molarity times the volume, and we're going to say that's X. Okay, we keep reading. Would you need to prepare? So 100 mils of 0.4. So those two pieces of information go together. So 0.4 molarity and then 100 mils for the volume. When you use this equation, it is okay to leave your volume in milliliters, okay, because they'll cancel out and everything will work out. But when you're using just molarity by itself, that one has to be in liters, okay? All right, so let's finish out the math, and you're going to solve for X. Okay, so X will equal, so 0.4 molarity times the 100 mils. All right, then of course, you're going to divide by the 2 molarity on both sides. All right, so put this in your calculator, 0.4 times 100 divided by 2. Okay, so then you should get, let me double check my answer, 0.4 times 100, and then divide by 2. Okay, so then your X should equal 20, and then we're solving for volume, and the volume here that we kept was in milliliters. Okay, 20 milliliters. All right, so let me explain to you what this equation is telling you. Okay, don't forget, our X, which was over here, is telling us how much of the stock solution we're going to use. So notice we solved that it is going to require 20 mils of stock solution. Okay, and then notice in this equation, you're not necessarily calculating the amount of water that you're adding, but you can obviously figure it out, all right? So if we want a total volume of 100 milliliters, so if we want a total of 100 milliliters and 20 of it is coming from the very concentrated stock solution, then how much is actually water? Well, like 80 mils, right? 80 mils would actually be of water. Okay, so let me kind of explain to you, let's draw a picture of this whole dilution here of what this would look like. Typically for a dilution, we use what is called a volumetric flask. So a volumetric flask has a very long neck, okay, it kind of looks like this. So it's a piece of glassware, okay, and these come in many different sizes. All right, these come in many different sizes. So if we wanted a total of 100 mils of this solution, then we would get a 100 mil flask, okay? We would find a 100 mil volumetric flask. Once again, these come in many different sizes. We have little baby ones that are like 10 mils, and then we have like giant ones that are like 2 liters. So the volumetric flask only has one calibration mark on the neck of the flask. So if this is a 100 mil volumetric flask, then when it is filled to the line, then you know it contains 100 milliliters. Okay? It would contain 100 milliliters. So then this particular problem, what we would do is we would add our solute, so or the concentrated solution, which we found was what? The 20 mils of the stock solution. All right, so we would add our 20 milliliters of the 2 decimal of the 2 molarity stock solution. Okay, we would add 20 mils of that. And then we would just fill, so once that gets in there, we would just fill the rest up with water until we get to that calibration mark, the 100 mil mark, okay? So then notice we're not really measuring the amount of water directly. We can just fill up the flask, the remaining amount, with water, and then we have the total amount that we needed. Okay, we only wanted 100 mils, and then when we dilute it with water, it would give us that correct concentration of 0.4. All right, so that is kind of, and then we would shake it or stir it, and then our dilution would be done. So that's one way we would actually make the solution. Okay, this is the very last way that we could measure concentration, by using a percentage, okay? So instead of using molarity, some solutions use a percentage. For example, hydrogen peroxide. If you ever buy hydrogen peroxide at the grocery store, it's usually like 3% hydrogen peroxide. Or if you buy rubbing alcohol, which is isopropyl alcohol, it's like 90% or 70%. So we can use percentages to represent concentration. So these are just a few different percentage type of equations. So if you want to do a percent by volume, it's volume of solute over the solution volume, okay? Or we might do what is called a mass volume percentage, which is the mass of solute over the volume of solute, okay, or solution, sorry. And so that would be listed as grams per milliliter. And in many cases, we would just use our basic concept of percentages part over whole, okay? So all of these would work for concentration. So part over whole, then of course times 100 to put it into the percent form. So we're going to do a sample problem. All right, so what is the percent, okay, what is the percent by volume of ethanol in the final solution when 85 mils of ethanol is diluted with 250 mils of water? Okay, so we want to calculate percent. So we can use our concept of part over whole. Okay, we want to know what is the percent by volume of ethanol. So then ethanol is our part. So how much ethanol do we have? Well, let's read the problem. It says we have 85, right? Oops, pen. So the part is 85 mils. Okay, so that's our part. So that is our percentage of ethanol. Is going to be the 85 mils of ethanol over the whole thing. Okay, so it says that the 85 mils of ethanol is diluted with 250 mils of water. Okay, so part over whole. So that's the part, and then the whole is going to be the 85 plus the 250. Okay, so 85, and then add the 85 and 250 together, and let's see what you get. Let's see, calculator. So 85 plus 250. Okay, so that turns out to be 335. And then you're going to multiply by 100 to get that into the percent form. So let's finish out the math. Okay, so then that should turn out to be approximately 25.4%. Okay, so that's how you do a percent problem. Just your typical part over whole times 100 to get into the percent form. All right? Okay, so that is everything for section 2. Those are all the different ways you could calculate concentration. And then we only have one more section left that we will talk about in a couple of days. Okay? All right, so see you later. Bye.